Tonight, as you settle into a comfortable position and let the weight of the day loosen its hold on your mind, I invite you to drift into a world where even the most powerful forces of nature reveal their quiet, gentle side. Lightning, a phenomenon often associated with intensity and sudden bursts of energy, can also be understood through a softer lens, one that highlights its elegance, its delicate structures, and the serene science behind every luminous flash. Before you ease into sleep, imagine yourself watching a distant horizon under a heavy sky. The air is calm, the world lies still, and the only movement is the slow drifting of clouds. Far away, you notice a faint flicker, silent, soft, almost shy. This is lightning at its most peaceful, a natural display that unfolds high above the earth with no urgency, no chaos, only quiet beauty. From this distance, each flash feels less like a disruption and more like a gentle reminder of the planet's ever moving rhythms. As the sky pulses faintly, you begin to see lightning not as a sudden explosion, but as a whisper between clouds, a graceful exchange of electricity looking for balance, a soft glow illuminating the sky for the briefest moment before fading back into darkness. You're safe, you're warm, and all you need to do is listen as we explore the calming science behind this phenomenon. Slowly, softly, one detail at a time. Let your breathing slow, your shoulders drop, and your thoughts stretch out like the quiet landscape beneath a storm. Each fact will guide you deeper into ease, like distant flashes guiding you through the night. And as the world grows softer, so does the storm above it. Lightning, in all its brilliance, becomes a lullaby written across the sky, here to help you rest, dream, and drift gently toward sleep. Lightning is one of nature's most fascinating expressions of energy, a sudden release of electrical charge that lights up the sky with unimaginable precision. Yet when explained slowly, patiently, and gently, lightning becomes something else entirely, a serene, natural process shaped by balance, chemistry, physics, and the quiet movements of the atmosphere. In this soft exploration, we'll travel through its secrets not with urgency, but with calm curiosity. Tonight, you'll learn how lightning forms, why it behaves the way it does, and what hidden stories it carries within each flicker. We'll take our time, moving through each chapter at a pace that encourages your mind to relax and wander freely. You'll discover how lightning grows inside clouds like threads of silver blue light, how it moves between the earth and sky like a slow electrical conversation, and how it shapes landscapes over millions of years. Each piece of knowledge will unfold gently, like a cloud revealing the earliest glimmer of a distant storm. As we move from chapter to chapter, you won't need to concentrate or hold on to every detail. Just let the words flow past you like a soft breeze. The rhythm of the explanations, the natural pauses, and the imagery woven through the facts will help your body ease deeper into rest. This isn't a lecture, it's a quiet journey, a nighttime walk through the vast and peaceful world of atmospheric science. By the time we finish, you may already be asleep or floating between wakefulness and dreams. And that's exactly how this exploration is meant to feel: calm, unhurried, and deeply soothing. So let the comfort settle in. Let your breath match the slow cadence of this narration, and allow lightning, normally a symbol of power, to become your companion in relaxation. A soft glow in the distance, guiding you gently toward a state of deep, restorative sleep, high above the quiet surface of the earth, hidden within the drifting shapes of thick, towering clouds. Lightning begins its life in silence, far from the familiar brightness we see from the ground. The first stirrings of lightning are soft, invisible steps of electrical imbalance forming deep inside the atmosphere. To understand how lightning is born is to follow a delicate sequence of movements, slow, steady, and graceful, like watching a vast natural machine adjusting itself toward harmony. It starts with a cloud, but not just any cloud. Thunderclouds, known as cumulonimbus clouds, rise miles into the sky, stretching vertically like floating mountains. Within these enormous structures, temperatures shift dramatically. The base of the cloud might be warm, but as you travel upward, the air grows colder and eventually freezing. This layered environment creates a perfect space for small particles, tiny droplets of water, fragments of ice, and delicate snow crystals to drift past one another, gently brushing, colliding, separating, and meeting again. Each collision carries a small electrical consequence. When two particles touch, a bit of charge is transferred. Sometimes a crystal gains electrons. Sometimes it loses them. But the important detail is that these charges begin to separate inside the cloud. Heavier particles, often negatively charged, fall toward the lower regions. Lighter ones, carrying positive charge, float upward. This sorting happens gradually, quietly, over and over again, until the cloud becomes a layered world of electrical imbalance. The top shines with gentle positive charge, while the bottom grows increasingly negative. This imbalance doesn't make noise. It doesn't flash or rumble. It simply builds, like the slow inhale of a long breath, and the air around these regions begins to feel the tension between charges, an invisible pull, a difference waiting to be resolved. On a calm night, if you could float within the cloud, you wouldn't see chaos. You'd see tiny ice crystals tumbling peacefully, drops of water gently rising and falling, and an unseen pattern of electricity weaving itself through the softness. Eventually, the imbalance becomes too great. The cloud can no longer hold the separation it has built. Nature prefers balance, prefers ease, prefers a state where energy can move freely rather than stay trapped. So, the negative charge at the base of the cloud begins to reach outward, searching for a path to release the tension. It doesn't reach all at once. Instead, it explores in small, branching steps, thin threads of electrical potential known as stepped leaders. A stepped leader is one of the most delicate phases of lightning's birth. It forms a faint, branching path through the air, moving downward in quiet, nearly invisible segments. Each segment is only a few dozen meters long, pausing briefly before extending again. To us on the ground, this process happens far too quickly and subtly to see. But inside the cloud, it unfolds like a slow, patient search, feeling its way toward an opposite charge. While this negative branch reaches downward, the earth below responds. The ground, trees, buildings, and even the tips of blades of grass sense the growing electrical tension above them. In response, they begin to release small upward reaching streams of positive charge called streamers. These streamers stretch upward, trying to meet the descending leader, almost like gentle hands reaching toward an approaching spark. When one of these streamers meets the descending leader, the connection is complete. For an instant, a channel forms, a bridge between the sky and the earth. And in that exact moment, lightning is born. The brilliant flash we see is not the leader itself, but the sudden, fast flow of energy racing upward through the channel that has been formed. This powerful return stroke, traveling from ground to cloud, is what lights up the sky. But inside the cloud, there is more to the story. Many lightning strikes never reach the ground at all. In fact, most lightning happens entirely within the cloud itself, traveling between the layers of positive and negative charge. This intra-cloud lightning often looks like a gentle flicker illuminating the cloud from within, a soft, glowing pulse that spreads through the vapor like a lantern behind a curtain. These flashes are quieter, more diffuse, and sometimes more beautiful in their subtlety. They reveal the structure of the cloud, its folds, its depth, its hidden towers rising toward the upper atmosphere. Intra-cloud lightning is born from the same dance of charge separation, but instead of reaching downward, the electrical energy seeks balance within the cloud. It might travel horizontally across the sky, bridging regions of charge like a whispered conversation between distant parts of the storm. From the ground, these flashes appear as soft glimmers, lighting the clouds in breathtaking patterns. They are the quiet heartbeats of a storm, not loud, not sharp, simply luminous. Another form of lightning, known as cloud to cloud lightning, links two separate clouds. Imagine two great floating continents in the sky, each carrying their own imbalance of charge. When conditions are right, a bolt may leap between them, forming a sudden connection that travels miles through open air. Though these flashes can be dramatic, they often appear to us as distant illuminations, muted and gentle when observed from afar. High within the atmosphere, lightning can take even stranger, more ethereal forms. Sprite lightning, for example, appears above thunderstorms as delicate, red-tinted shapes, thin tendrils, branching forms, and ghostly flashes that drift downward from near space. Sprites are fragile, lasting only a few milliseconds, and they occur too high for the thunder to accompany them. Their appearance is soft, almost dreamlike. But even these strange upper atmosphere events begin with the same fundamental idea: electrical imbalance seeking release. At each stage of its birth, lightning remains a process deeply rooted in the natural desire for balance. The cloud collects charge, the air allows pathways to form, the earth responds, and the eventual release of energy is a return to equilibrium. This entire cycle, from the first collisions of ice to the final bright flash, occurs in a matter of seconds, but understanding it slowly, gently, brings a sense of calm, a sense that even the most powerful natural forces move according to rhythms, predictable, graceful, and patient. When you watch lightning from a safe and quiet place, the flashes seem almost like breathing. The cloud brightens, it fades, it glows again. Each pulse is a silent reminder of the processes unfolding many miles above you. Even though each bolt carries immense energy, the creation of lightning is not violent in its essence. It is the atmosphere adjusting itself, balancing charge, following laws of physics that operate smoothly and reliably. As the storm continues, building lightning, more and more of these leaders form inside the cloud. Some reach sideways, some downward, some upward. They weave through the air like branching roots or delicate cracks forming in glass. They are the cloud's internal electrical architecture, beautiful, complex, and constantly shifting. One fascinating aspect of lightning's birth is that the air around the leader becomes temporarily more conductive than usual. The intense electric field rearranges oxygen molecules, forming narrow channels where electricity can flow with astonishing speed. For a brief moment, the sky becomes a sculpted path of ionized air, an invisible roadway waiting for the returning surge of light. By the time the bright flash finally appears, most of the work of lightning has already happened. The charge has separated, the path has formed, and the bridge between regions of imbalance has been established. The flash is simply the moment it all becomes visible. And even then, the bolt is often much brighter and faster than the brain can fully process. What looks like a single strike is often multiple return strokes traveling along the same path in rapid succession, each one lighting up the sky with extraordinary clarity. Inside the clouds, after the energy moves through, the electrical landscape begins to reset. More collisions occur, more charges separate, and the cycle begins again, quiet and steady. A storm might produce thousands of lightning flashes, each one born through the same patient buildup and sudden release. Understanding the birth of lightning in this slow, gentle way makes it feel less like a sudden shock and more like a natural breath of the earth, a rhythm, a pulse, a soft glow traveling through the sky as the atmosphere settles itself. In this light, lightning becomes not just a spectacle, but a reminder of the beauty hidden in even the most powerful natural processes, a beauty you can drift into, relax with, and gently fall asleep to. Lightning may appear sudden and unpredictable, but behind each lies a quiet foundation of physics, steady, patient, and beautifully structured. While the striking glow catches our attention, the true nature of lightning lives in the invisible mechanisms that guide every step of its formation. To understand lightning through the lens of physics is to slow down the process, observing not just the brightness, but the gentle movements of electrons, the subtle forces between particles, and the calm balance that nature continuously seeks. At the heart of lightning is electric charge, one of the simplest and yet most profound concepts in physics. Every particle in the atmosphere carries either a positive, negative, or neutral charge. Lightning occurs when charges separate over a large region and then seek to reunite. But this movement is never chaotic. It follows predictable, elegant laws. The atmosphere becomes like a vast electrical canvas where charges drift, gather, repel, and attract in the most delicate ways. Inside the cloud, ice crystals and water droplets collide and exchange charges. These exchanges create layers. The upper part of the cloud becomes positively charged, while the lower part becomes negatively charged. The separation creates an electric field, an invisible stretch of force between regions of different charges. This electric field becomes stronger and stronger as the imbalance grows. One of the most calming ways to visualize an electric field is to imagine it as a gentle tension in the air, similar to the quiet stretching of a rubber band. The more charge separates, the tighter the stretch becomes. The air resists at first, acting as an insulator, but like a rubber band pulled too far, there comes a moment When the tension becomes too great, the air can no longer hold the opposing charges apart, and a pathway begins to form where electricity can flow. This pathway begins with the stepped leader, which travels through the sky in small, branching steps. Each step is a response to the electric field around it. In physics terms, the leader forms because the intense electric field breaks down the insulating properties of the air. The air molecules become ionized, stripped of their electrons, creating channels that conduct electricity more easily. It is as though the air is gently reshaping itself to allow the charges to reconnect. The electric field plays a crucial role in guiding the leader. It directs the path of least resistance, the route where the air is easiest to ionize. The leader does not rush. It progresses in quiet stages, pausing between each step as though contemplating its next move. This delicate motion is governed by the slow buildup and release of microscopic discharges, tiny sparks too small to see, yet essential for shaping the eventual lightning bolt. Meanwhile, the ground responds to the charged leader descending from the cloud. Positive charge in the earth begins to accumulate, rising toward the approaching negative charge. Trees, buildings, and even small objects like fence posts become sources of upward reaching streamers, thin lines of charge that stretch toward the sky. These streamers form because the electric field from the cloud intensifies as the leader gets closer, encouraging the ground to send up its own connection. When a streamer and a stepped leader meet, a complete channel is formed. This exact moment is when the bright lightning flash becomes visible. The return stroke, an upward surge of electrical energy, travels at incredible speeds, reaching tens of thousands of miles per second. But despite its speed and intensity, the physics governing this motion remain calm, structured, and predictable. The brightness of lightning is caused by the intense heating of the air as electricity flows through it. The temperature in the channel can reach around 30,000 Kelvin, 5 times hotter than the surface of the sun. But even this extreme heat follows a gentle principle: the conversion of electrical energy into light and thermal energy. The channel expands rapidly, which creates the shock wave we later hear as thunder. However, the light itself appears instantly, illuminating the sky with a clarity shaped by the physics of gases, plasma, and energy transfer. Lightning also reveals the beauty of plasma physics. Plasma is sometimes called the fourth state of matter, beyond solid, liquid, and gas. During a lightning strike, the air becomes so energized that electrons break free from their atoms, creating a glowing, electrically conductive state. Plasma conducts electricity effortlessly, allowing massive amounts of charge to flow through the channel in a fraction of a second. As the energy dissipates, the plasma cools and the air slowly returns to its normal state. Once again quiet, once again still. Another gentle detail of lightning physics is the concept of electrical potential, also known as voltage. Lightning forms because the difference in charge between two regions becomes so large that electricity feels compelled to move. Voltage can be thought of as electrical pressure, a gentle push, encouraging electrons to flow toward a region where they are less concentrated. In a thunderstorm, this pressure builds gradually as charges separate, creating a natural inclination for balance. The Earth itself influences the physics of lightning. Its surface tends to carry a negative charge, while the atmosphere above it carries a positive charge. This natural configuration, known as the Earth's electric field, always exists, even on calm, cloudless days. Thunderstorms amplify this field, pulling charges further apart and increasing the electrical tension that leads to lightning. In many ways, a lightning strike is just the atmosphere restoring the balance between earth and sky. Even the shape of the lightning bolt follows physical laws. The branching, zigzag patterns result from variations in air resistance along the path of the leader. The electric field is not uniform. Small pockets of moisture, dust, or temperature differences can influence the direction of the channel. The bolt divides into multiple branches because electrical energy often explores several possible routes before settling on the easiest one. Each branch is a momentary attempt to find balance, a tiny search for the ideal pathway. Sometimes, lightning travels upward rather than downward. This happens when tall structures, such as towers or skyscrapers, generate strong upward streamers before a downward leader fully forms. Upward lightning follows the same physics: ionized channels, electric fields, plasma formation, just in reverse direction. From a distance, these upward bolts look like delicate silver strands rising toward the clouds. The physics also explains why lightning flashes multiple times along the same path. After the main return stroke, the channel cools but remains partially ionized. If the cloud still contains excess charge, another pulse of energy may travel down the same channel. These repeated strokes create the flickering effect that gives lightning its shimmering beauty. Each stroke is like a gentle breath of the storm, exhaling until the tension is finally released. Perhaps one of the quietest and most serene aspects of lightning physics lies in how quickly the atmosphere returns to calm. After the flash fades, the electric field begins rebuilding slowly. Charges separate again, collisions continue inside the cloud, and the process prepares for another cycle. This rhythm, build up, release, rest, is the atmosphere's natural way of keeping itself in balance. When understood through physics, lightning becomes less of a sudden shock and more of a graceful expression of energy moving through the sky. Each step, from charge separation to the formation of plasma, follows the principles of nature with remarkable precision. What seems chaotic from afar is, in truth, a carefully choreographed dance of particles and forces unfolding silently inside the storm. As you relax and let these ideas settle in your mind, you may feel the calm rhythm behind each fact, the quiet buildup of charge, the slow formation of pathways, the brief flash of connection, and the peaceful return to stillness. Lightning, when viewed softly, becomes a symbol of balance restored, a reminder that even the most powerful natural phenomena move according to gentle laws that shape our world. High above the landscape, far removed from the familiar sounds and movements of daily life, storm clouds gather in slow, deliberate formations. These towering, majestic clouds, sometimes rising higher than the tallest mountains on earth, hold within them the quiet machinery that powers every lightning strike. But despite the dramatic appearance of these clouds, the processes that charge them with energy are gentle, patient, and deeply rhythmic. Understanding how storm clouds build the energy for lightning is like watching a vast natural engine hum softly in the sky. Everything begins with warm, moist air rising from the surface. On a warm day, Sunlight heats the ground, which warms the air above it. As this air becomes lighter, it begins to rise, slowly at first, then steadily, forming invisible columns that climb higher into the atmosphere. This rising air is known as an updraft, and it is one of the most essential ingredients for storm formation. As the moist air ascends, it cools. The water vapor it carries begins to condense into tiny droplets, creating the first wisps of cloud. These small puffs gather and thicken as more and more air rises beneath them, adding layers upon layers of moisture. The cloud grows upward, expanding like a soft, cotton like structure, stretching toward the sky. With each additional layer, the cloud becomes denser, more complex, and more capable of storing electrical energy. Deep inside the cloud, temperatures vary greatly depending on altitude. Near the base, the air may still be warm enough for liquid droplets to remain. Higher up, the air becomes cold enough for ice crystals to form. Still higher, supercooled water droplets, liquid even below freezing, float gently among the crystals. This mixture of moisture in different forms creates the ideal environment for electrical charge to accumulate. The process begins with collisions. In the churning environment of the cloud, droplets and ice particles bump into each other millions of times. Some particles grow larger as they freeze or collect moisture, while others remain small and delicate. Each collision transfers a tiny bit of electrical charge. The direction of charge transfer depends on temperature, size, and composition. Larger particles often take on negative charge, while smaller crystals gain positive charge. Gravity assists in separating these charged particles. Heavier, negatively charged particles fall toward the lower part of the cloud, while lighter, positively charged ones drift upward. Over time, this separation becomes quite pronounced. The upper regions of the cloud glow, metaphorically, with positive charge. The lower regions grow increasingly dense, with negative charge. These layers can stretch for miles, creating massive reservoirs of electrical potential. Meanwhile, the rising and falling currents of air inside the cloud continue reshaping this internal structure. Updrafts carry moisture upward, cooling it, freezing it, and lifting positive charges higher into the atmosphere. Downdrafts, currents of cold air sinking through the cloud, bring negatively charged particles downward. The entire cloud becomes a dynamic system of circulating air, moving water, and drifting charge. Despite the magnitude of these movements, the process is incredibly quiet. From within the cloud, there is no roar or violent shaking, only the soft movement of particles and the gentle drift of moisture. The cloud breathes, in a sense, rising and falling with currents of air. And with each breath, the electrical charges become more separated, more intense, and more ready to discharge. As the charge separation increases, the electric field inside the cloud strengthens. An electric field is a kind of invisible tension, a stretching force between regions of opposite charge. The more the charges separate, the stronger the tension becomes. Eventually, the tension grows so great that the air between the charges begins to feel strained. The insulating properties of the air weaken, and small pockets of ionized gas begin to form. This is the stage when the cloud becomes electrically ripe for lightning. But the cloud does not release this energy immediately. Instead, it continues building charge in the background, allowing the tension to rise to a critical point. The air within the cloud becomes filled with potential energy, energy waiting for a path to flow, waiting for balance to be restored. During this buildup, the cloud interacts with the surface of the earth below it. The negative charge at the cloud's base induces a positive charge in the ground directly beneath the storm. This induced charge rises to the tops of trees, buildings, and even the surface of the soil. The ground becomes part of the electrical system, preparing silently for the moment when the sky will attempt to connect with it. But even before lightning reaches toward the earth, energy is exchanged within the cloud itself. Intra-cloud lightning, the most common form, releases the tension between its upper and lower layers. When this happens, the cloud lights up from within, like a lantern glowing softly behind a veil. These flashes reveal the internal architecture of the storm, its pillars of vapor, its hidden towers, and the swirling paths of charged particles caught in their endless dance. The buildup of electrical energy inside the cloud also influences its shape and behavior. Strong updrafts create massive vertical columns called cloud towers, which can extend up to 12 kilometers into the atmosphere. These towers contain powerful currents that lift ice crystals and droplets with great efficiency, accelerating the separation of charges. In especially tall clouds, the tops spread outward, forming the iconic anvil shape seen in mature thunderstorms. This towering structure is not just beautiful, it's a sign of immense electrical potential. The greater the height of the cloud, the larger the electric field it can support. The cloud becomes a vast, floating power reservoir, charged by the gentle but persistent motions of air and water. Another important element in storm energy buildup is humidity. High humidity allows more water vapor to rise into the storm, fueling larger updrafts and producing more collisions. The result is a more intense separation of charge and a stronger electric field. Even small changes in humidity can enhance or weaken a storm's ability to produce lightning. Wind shear, the variation of wind speed and direction at different altitudes, also plays a role. Shear helps organize the storm's internal structure, creating rotating columns of air that strengthen updrafts. These rotations increase the number of particle collisions, and therefore the amount of charge separation. In many ways, wind shear helps a storm become more electrically efficient. As all these processes unfold inside the cloud, the atmosphere surrounding it begins to respond. The air outside the storm senses the building electrical tension and adjusts accordingly. Nearby clouds may develop small charges. The ground may become increasingly positively charged. Even the air molecules in the space between the cloud and Earth begin aligning themselves with the growing electric field. Inside the cloud, the entire system reaches a point where the electrical energy is ready to be released. But rather than erupting instantly, the release begins with a small, quiet step, the formation of a stepped leader. Like a whisper of electricity reaching into the air, the leader forms the first path through which charge can move. It is the beginning of a gentle cascade that will soon illuminate the sky. The storm cloud, through nothing more than rising air, falling particles, and the laws of physics, has prepared itself for this moment. The vast electrical charge it has accumulated will soon flow through the atmosphere, creating a flash of light that reveals the beauty and complexity of everything that has been building quietly within it. But the story of how storm clouds charge themselves is not about violence or chaos. It is about balance. It is about the atmosphere finding ways to manage energy through simple, natural processes. It is about the rhythm of the sky, slow, persistent, and always moving toward equilibrium. In this soft perspective, the buildup of lightning energy becomes calming rather than alarming. It becomes a reminder of nature's gentle cycles, a reminder that even the most powerful storms are shaped by delicate movements, tiny droplets, drifting ice, rising air, and by the quiet physics of a world always seeking harmony. Lightning is often imagined as a single phenomenon, one bright flash that crosses the sky in a jagged line. But in truth, lightning expresses itself in many different forms, each one following its own quiet pattern, its own graceful path through the atmosphere. Some types of lightning stay hidden within clouds, illuminating their shapes softly from the inside. Others stretch across the sky in delicate horizontal lines. Some reach toward the ground, while others rise upward toward the clouds. Some occur so high in the atmosphere that they resemble glowing red ripples rather than bolts. Understanding these varieties helps us see lightning as a diverse, layered phenomenon, one that behaves with subtlety and elegance. Intracloud lightning, the most common type, remains gently contained within the cloud itself. Rather than reaching toward the earth, it travels between regions of positive and negative charge inside the storm. From the ground, this type of lightning often appears as a soft glow spreading through the cloud, as though someone has lit a lantern behind a curtain of vapor. Its patterns are varied. Some resemble branching veins of light, while others form broad, diffused flashes that reveal the internal texture of the storm. Because intracloud lightning rarely creates loud thunder close to the viewer, it often feels more peaceful, like a distant pulse of light rather than a sharp interruption. Closely related is cloud to cloud lightning, which forms bridges of light between two separate clouds. These bolts stretch horizontally across the sky, connecting distant regions of charge. From a distance, they look like quiet streaks of light, linking floating islands in the atmosphere. These horizontal bolts can travel dozens of miles, moving gracefully across large expanses of sky without ever touching the ground. Their movement emphasizes the interconnectedness of storm systems, showing how clouds communicate electrically across vast spaces. Another gentle form of lightning is sheet lightning, named for the way it illuminates large areas of the sky. Instead of a visible bolt, viewers see the entire horizon brighten for a moment. This effect happens when the lightning is hidden behind clouds or beyond the observer's visual range. The light diffuses through the atmosphere, creating a broad, even glow. Sheet lightning can feel calm and distant, like the soft flicker of a candle. It often occurs during nighttime storms, when the sky becomes the canvas for wide, muted flashes that drift in and out of view without revealing their source. Then there is heat lightning, a phenomenon often misunderstood. Many people believe heat lightning occurs because of hot temperatures, but in reality, it is simply the glow of distant thunderstorms, too far away for the thunder to be heard. On warm summer nights, heat lightning appears as silent flashes on the horizon. No bolt is visible, and no sound follows, just a quiet flicker far away, signaling that a distant storm is active. The light travels farther than sound, allowing us to see the storm long after the thunder has faded. Heat lightning has a dreamy, peaceful quality, almost like the sky is blinking slowly in the distance. One of the most dramatic types of lightning is cloud to ground lightning, the form most people recognize. But even this powerful variety begins gently, with a stepped leader reaching downward in quiet, branching increments. When the connection is made, the return stroke travels upward with great intensity. Yet, from afar, even cloud to ground lightning can appear serene. The bolt descends in a graceful, branching pattern, illuminating the scene for a brief instant. Some cloud to ground bolts branch widely, forming intricate networks of light that resemble the roots of a tree. Others remain simple and direct, a single pathway from cloud to earth. Within cloud to ground lightning, there are positive and negative strikes. Negative lightning is far more common, carrying electrons from the cloud to the ground. Positive lightning is rarer but often more powerful. It originates from the upper, positively charged layers of the cloud, traveling much farther to reach the ground. Despite its strength, positive lightning follows the same gentle principles: separation of charge, formation of leaders, and the quiet building of electrical tension. Another beautiful variation is ribbon lightning. This occurs when strong winds push each successive return stroke slightly sideways, creating the appearance of parallel ribbons of light. Ribbon lightning feels almost like a slow motion photograph, with the bolt stretched gently across the sky in delicate layers. Though the movement happens quickly, the visual impression is one of softness and spread, as though the lightning has blurred into horizontal threads. Bead lightning is another special form, appearing as a series of bright segments rather than a continuous line. While the channel is cooling, it becomes briefly uneven in brightness, creating bead-like structures along the bolt. Some observers describe bead lightning as resembling a string of pearls, each glowing momentarily before fading. This form is not separate from normal lightning, but rather a transitional phase occurring during the dissipation of energy. Still, its appearance has a quiet beauty, giving the sense of the bolt dissolving gently into the night. Then there is the rare and mesmerizing ball lightning. This phenomenon appears as a glowing sphere of light, often moving slowly and unpredictably through the air. Although ball lightning is still not fully understood by science, reports describe it as silent or gently humming, drifting with a dreamlike motion. Some spheres appear to fade gradually, while others vanish suddenly. Because ball lightning is so rare, it carries an air of mystery, like a soft, wandering lantern created by the storm. High above the clouds, even more unusual forms of lightning dance in the thin, cold air. These upper atmospheric events include sprites, jets, and elves, each with their own ethereal shapes. Sprites are delicate, red flashes that resemble jellyfish or branching tendrils descending from the upper atmosphere. They occur above powerful thunderstorms, triggered by the electrical activity within the storm below. Though they last only milliseconds, sprites often appear soft and wispy, like faint red feathers suspended in the sky. Blue jets, on the other hand, rise upward from the tops of storms, forming narrow cones of blue light that shoot toward the stratosphere. Unlike typical lightning that moves downward, jets climb into the upper atmosphere, glowing quietly as they ascend. Their color comes from nitrogen molecules excited by the electrical energy, creating a soft blue hue that blends gently with the night sky. ELVs, short for emission of light, and very low frequency perturbations due to electromagnetic pulse sources are even more delicate. They appear as enormous, expanding rings of light spreading outward horizontally at tremendous speeds. The rings are faint and fleeting, lasting less than 1,000th of a second, yet their shape is wide and smooth, creating a brief halo-like glow high above the earth. Ice crystal lightning is another subtle form that occurs in regions of extremely cold air. In these environments, lightning may take on softer, shorter shapes with less branching and more diffuse glow. The cold air alters the conductivity of the channel, shaping the bolt into a more subdued pattern. There is also volcanic lightning, which emerges from the ash plumes of erupting volcanoes. While volcanic eruptions are dramatic, the lightning within them follows the same gentle principles of charge separation. As ash particles collide, they exchange charges, creating small electrical imbalances that lead to lightning within the plume. From a distance, volcanic lightning resembles delicate sparks glowing within drifting clouds of ash, a rare and mesmerizing sight. Each type of lightning has its own signature, its own rhythm, and its own beauty. Some forms illuminate the sky in strong vertical lines. Others stretch horizontally across distant clouds. Some glow red, some blue, some white. Some are visible for miles, while others hide softly behind the clouds. But all of them share the same essential qualities. They are natural expressions of balance, shaped by physics, guided by charge, and born from the quiet interactions of particles in the atmosphere. Seeing lightning through this gentle lens helps transform the phenomenon from something startling into something soothing, a reminder that even when the sky lights up with brilliance, the processes behind each flash are slow, steady, and deeply harmonious. Lightning becomes not a symbol of chaos, but a symbol of connection between clouds, between air layers, between earth and sky, and between the forces that shape our world. When lightning flashes across the sky, it happens so quickly that the entire journey seems instantaneous, a sudden streak of light that appears and disappears before the mind can fully register its shape. But when we slow the moment down, observing gently and patiently, we discover that lightning follows a surprisingly delicate path. It travels not in a single continuous line, but through a series of quiet steps, guided by subtle forces and shaped by the atmosphere's invisible patterns. Understanding how lightning travels is like watching the sky trace an intricate map, one careful movement at a time. The journey begins long before the visible flash. Inside the cloud, the electric field builds steadily as charges separate. The air resists at first, acting as an insulator that keeps the charges apart. But as the imbalance grows, the insulating power of the air begins to weaken. Molecules polarize, aligning themselves with the electric field. A subtle tension fills the atmosphere, like the gentle stretching of a thread. When the tension becomes too great, the air cannot hold the charges apart anymore. A narrow path begins to form. This first stage of travel belongs to the stepped leader. The stepped leader is a faint, branching trail of ionized air that moves toward the opposite charge, not quickly, but in a series of small, thoughtful steps. Each step is roughly 50 meters long, and each pause between steps lasts about 50 millionths of a second. To us, this seems instant, but within each microscopic pause lies a quiet negotiation between the atmosphere and the charge. The leader is exploring the air, searching for the route of least resistance. As it travels, the stepped leader creates a network of branching channels. Some branches stretch outward briefly, only to fade. Others travel farther, sensing regions where the electric field is stronger. The leader is not a single bolt, but a collection of potential routes, each one a possibility for where the lightning might eventually flow. Observing the stepped leader in slow motion would look like delicate fingers of light reaching cautiously into the sky. Meanwhile, the ground responds as the negatively charged leader descends from the cloud. The positive charge on the Earth's surface gathers beneath it. This positive charge travels upward, concentrating at the tallest points: trees, buildings, hilltops, even the tops of individual blades of grass. These upward reaching threads of charge are called streamers. They stretch toward the descending leader like subtle sparks, reaching for connection. When one of these streamers meets a branch of the stepped leader, the path becomes complete. In that instant, lightning finds its bridge, a continuous channel linking cloud and ground. This is when the second stage begins, the return stroke. The return stroke is what we see as the bright lightning bolt. But despite its brilliance, the return stroke is still shaped by the gentle principles of electricity seeking balance. The return stroke travels upward, not downward, moving from the ground through the channel toward the cloud. It is incredibly fast, sometimes reaching speeds of 100 million meters per second. The channel brightens as electrons flow rapidly, heating the air to temperatures hotter than the surface of the sun. But this intense energy follows the same graceful path created earlier by the stepped leader. The bright flash is just the atmosphere smoothing out the imbalance of charge, returning everything to equilibrium. Often, the process doesn't end with a single stroke. The channel remains partially ionized for a moment, making it easier for additional pulses of charge to travel through. These pulses, called subsequent strokes, create the flickering effect sometimes seen in lightning. Each stroke travels upward along the same pathway, giving the appearance of a bolt that flashes several times before fading. The flicker is a sign not of chaos, but of repetition, as the cloud releases its energy in soft, rapid waves. Some lightning travels in different directions. Not all bolts move straight from cloud to ground. In fact, the majority of lightning stays within or between clouds. Intra-cloud lightning travels between layers of opposite charge inside the storm. From inside the cloud, these bolts weave horizontally, like glowing roots spreading through the sky. From below, they appear as soft flashes that illuminate the cloud's interior. Cloud-to-cloud lightning stretches across the open sky, connecting two separate clouds. These bolts can travel astonishing distances, sometimes more than 50 kilometers. They move horizontally, guided by the electric fields between storm cells. From the ground, they look like delicate threads, linking distant islands floating in the sky. Sometimes, lightning begins from the ground and travels upward. Upward, lightning occurs most often around tall structures such as communication towers or skyscrapers. When the electric field around the structure becomes strong enough, a streamer rises from the ground before a downward leader has fully formed. The bolt then propagates upward into the cloud. Upward, lightning has a smooth, graceful appearance, often lacking the dramatic branching seen in downward strikes. Another form of lightning travels not through the lower atmosphere, but into the upper reaches of the sky. Sprites, for example, travel downward from the mesosphere in wispy, red tinted patterns. These forms of lightning move differently than typical bolts because the thin air at high altitudes affects the electrical conductivity. Sprites descend quickly, branching into delicate filaments that resemble jellyfish tentacles or coral like structures. Their movement is quiet and diffuse, spreading gently across the upper sky. In contrast, blue jets rise upward from the tops of storms, shooting toward the stratosphere in narrow cones of electric blue. Their motion is smoother and more direct than cloud to ground lightning, following a straight upward line. Elves, the faint, expanding rings of light in the ionosphere, travel horizontally at extraordinary speeds, forming a rapidly widening halo that vanishes almost immediately. But even with all these variations, the underlying principle remains the same. Lightning travels along the path where the atmosphere is most ready to conduct. This path is shaped by the electric field, the ionized air, and the movement of charges seeking balance. Everything about lightning's journey, from the tentative steps of the leader to the bright flash of the return stroke, is guided by this natural inclination toward equilibrium. Once the flash fades, the channel collapses gently. The ionized air cools. Molecules return to their normal states. The electric field weakens. For a moment, the sky rests. But inside the cloud, new collisions of ice and droplets begin to separate charges once again. The atmosphere prepares quietly for the next flash, building energy in slow, steady cycles. Understanding how lightning travels reveals its elegance. Instead of a sudden streak of chaos, it becomes a series of calm, predictable movements shaped by the physics of air and charge. Each bolt is a journey, beginning with tiny, silent steps inside a cloud and ending in a brief, brilliant moment where the sky restores its balance. Seen this way, lightning becomes peaceful rather than startling, a soft reminder that even the most dramatic events in nature unfold through gentle processes, guided by laws that operate quietly behind the scenes. The path lightning follows is not random, it is the sky choosing the easiest way to return to calm. And in watching it, or even imagining its motion, we can feel a similar calm settling over us, reminding us of the quiet patterns that shape our world. Although thunder is often described as loud, sharp, or startling, the science behind it is built on gentle, predictable principles. Thunder is not born from chaos, but from the natural reaction of air to a sudden change in temperature and pressure. And when we slow this process down, removing the rush, the intensity, and the surprise, we begin to see thunder as something softer, something rhythmic and atmospheric, shaped entirely by the quiet physics of air responding to light. To understand thunder, we must begin with the lightning bolt itself. Lightning is a powerful release of electrical energy traveling through a channel of ionized air. During this brief journey, the bolt heats the air to astonishing temperatures around 30,000 Kelvin, which is hotter than the surface of the sun. But this temperature rise doesn't last more than a fraction of a second. It is a quick, intense burst, followed immediately by cooling. When lightning heats the air expands, not slowly, the way a warm breeze spreads through a summer afternoon, but almost instantly. This sudden expansion pushes outward against the surrounding atmosphere. Imagine a soft, inflated cushion suddenly pressed outward from the inside. Every layer of air around it shifts in response. The rapid expansion creates a pressure wave, which moves outward in all directions. That pressure wave is thunder. It begins as a sharp, immediate displacement of air close to the lightning channel. But as the wave travels outward, spreading farther through the atmosphere, it slows, stretches, softens, and becomes the rolling sound we associate with distant storms. Thunder is not one sound, but many, each part created at different points along the lightning bolt's path. A long bolt creates a long, layered rumble because sound reaches the listener from different distances and angles. The reason thunder often sounds deep and rolling rather than sharp is because of the way sound waves behave in the atmosphere. As thunder travels, it interacts with the air, the ground, the clouds, and even the temperature layers above the Earth's surface. These interactions bend the sound waves gently, bouncing them, stretching them, and sometimes muffling them. A short, intense wave becomes a long, soft rumble. Even the shape of the lightning bolt influences thunder. Lightning is rarely a straight line. It branches, curves, and zigzags through the sky. Each segment of the bolt emits its own pressure wave when the air around it heats and expands. When these waves combine, they create a layered, textured rumble that can last several seconds. If you've ever noticed thunder arriving in distinct bursts, cracks, rumbles, rolls, it's because different parts of the bolt are different distances from you. The sound from the farthest section takes longer to arrive, while the nearest section reaches your ears first. In this way, thunder is like an echo of the lightning's entire path, arriving piece by piece. The timing between lightning and thunder also tells a gentle story about distance. Light travels almost instantly from the bolt to the observer at nearly 300,000 kilometers per second. Sound, however, moves much more slowly at around 343 meters per second in air. Because of this difference, we see lightning first, then hear thunder. Counting the seconds between the flash and the rumble reveals how far away the lightning occurred. About 3 seconds correspond to roughly 1 kilometer, an easy, rhythmic way to measure distance using nature's own clock. Thunder also changes based on how the lightning is positioned relative to the observer. A bolt directly overhead often creates a shorter, louder clap because the sound waves travel a shorter path through the atmosphere. A bolt several kilometers away produces a softer, rolling thunder because the sound waves have more time and distance to stretch out. When the bolt is hidden behind hills or trees, the ground itself can absorb some frequencies, creating a muted, distant tone. Temperature layers in the atmosphere further shape the sound. On warm, humid nights, thunder can travel farther because moist air carries sound well. In cool or unevenly layered air, thunder may fade more quickly or sound distorted. The Earth's surface also plays a role. Water surfaces reflect sound. Forests soften it, Open plains carry it gently across long distances. Every environment gives thunder its own unique character, its own voice. One quietly beautiful aspect of thunder is that it doesn't always sound the same from the beginning of a storm to the end. Early in a storm, when lightning often strikes higher in the clouds, thunder may sound faint or muffled. As the storm draws closer, the bolts may occur lower in the atmosphere or closer to the ground, producing clearer, fuller rumbles. And as the storm moves away, the sound gradually softens until it becomes no more than a distant whisper on the horizon. Thunder and lightning are directly linked, but their relationship is not chaotic. It is intimate and predictable. Lightning creates the conditions for thunder, and thunder tells the story of the lightning's path. They are two expressions of the same event, one seen, one heard, both shaped by the atmosphere's gentle reactions to energy. Some forms of lightning create unique types of thunder. For example, heat lightning, which is actually distant storm lightning, produces thunder that is too far away to be heard. The sound waves dissipate before reaching the observer, leaving only the soft glow on the horizon. This silent form of lightning feels tranquil, like a storm breathing quietly beyond the edge of the world. Large, branching bolts create long, layered thunder because their extended channels emit sound over a wide area. Short, simple bolts create brief bursts. Positive lightning, which originates higher in the cloud, sometimes produces thunder that carries a sharper initial crack, followed by a long roll. Yet even these louder events soften with distance, becoming gentler and gentler as the storm drifts away. Interestingly, thunder can also be reflected and refracted by the environment. When thunder echoes between mountains, valleys, or urban structures, it gains a rhythmic, repeating quality. These echoes create waves within waves, like ripples overlapping on a quiet lake. Although the initial sound is sharp, the echoes form soft patterns that fade gradually, as if the storm is slowly exhaling. In many ways, thunder is the atmosphere responding naturally to sudden warmth. When heated air expands quickly, it needs room to stretch. That expansion pushes surrounding air outward in a wave. When the wave reaches your ears, you hear thunder. It is simply the sound of air rearranging itself, restoring balance after being momentarily disturbed. Understanding thunder through this slow, quiet perspective transforms the experience entirely. Rather than seeing thunder as something harsh or startling, we can see it as a natural consequence of the sky's equilibrium being gently restored. The atmosphere breathes, adjusts, expands, and settles. Thunder is the sound of that settling. The next time you hear thunder, you may notice how many shapes it takes. The first sharp crack, the low rumble, the stretched out roll, the fading echo. Each sound is a different part of the bolt's path reaching you through the air. Thunder becomes a kind of map, a soft record of where lightning traveled, how far it stretched, and how the sky responded. In this slow understanding, thunder becomes comforting. It becomes a reminder of nature's rhythms, of energy moving gently through the world, of the sky finding its balance once more. And when paired with the soft glow of lightning, thunder completes the story. One part light, one part sound, both moving through the atmosphere like a quiet conversation between earth and sky. Lightning is often thought of as a momentary event, an instant of brightness followed by darkness, a brief pulse of energy that disappears almost as quickly as it appears. But when we look beyond the flash itself, we discover that lightning is part of a larger, quieter story. Over centuries, thousands of years, and even millions of years, lightning shapes the earth in subtle yet meaningful ways. Each bolt, no matter how small, participates in slow transformations that contribute to the landscape, the atmosphere, and even the chemistry of life. When understood through this long, gentle timeline, lightning becomes a patient sculptor, working softly across the ages. One of the most ancient and fascinating roles of lightning is its connection to the formation of life's building blocks. Scientists believe that billions of years ago, Earth's early atmosphere contained simple gases: methane, ammonia, water vapor, and hydrogen. When lightning passed through this mixture, it provided bursts of energy capable of rearranging these molecules. Experiments simulating early Earth conditions have shown that lightning can help produce amino acids, tiny organic molecules that form the foundation of proteins. Though each bolt contributed only a small amount, the process occurred over millions of years, creating a quiet accumulation of complexity. In this slow, patient way, lightning may have helped seed the earliest chemistry of life. Even today, lightning continues to play an essential role in the Earth's chemical balance. One of its most important contributions is the formation of nitrogen oxides, compounds that help fertilize the soil. The atmosphere is filled with nitrogen gas, but in its natural form, it is difficult for plants to use. When lightning heats the air, the intense temperature breaks apart nitrogen and oxygen molecules, allowing them to combine into new compounds. These compounds eventually fall to the ground in rain, enriching the soil with nutrients that plants need to grow. Each bolt contributes only a tiny amount of this natural fertilizer, but over time and across millions of flashes, lightning becomes a quiet caretaker of ecosystems. Lightning also shapes the planet through heat. When a bolt strikes sand, soil, or certain minerals, the sudden burst of heat can melt them instantly. As the melted material cools and solidifies, it forms glass-like structures called fulgurites. These delicate tubes, often hidden beneath the surface, preserve the shape of the lightning channel that created them. Some fulgurites are thin and fragile. Others are thick, branching forms that resemble roots or coral. They can remain buried for thousands of years, quietly recording a moment when lightning touched the earth. In this soft, geological sense, lightning leaves behind a signature, a frozen memory of its path through the ground. Through the ages, lightning has also influenced forests and landscapes in subtle ways. While some strikes ignite fires, most do not. But those that do can help shape ecosystems where fire is a natural part of the environment's rhythm. In certain forests and grasslands, small fires clear away dry material, make room for new growth, and open space for sunlight to reach the ground. Over centuries, this process supports biodiversity, allowing species adapted to fire to flourish. Even in this role, lightning acts not as a destructive force, but as a participant in the slow cycles that ecosystems rely on. Lightning can also alter rocks and minerals on an almost microscopic level. When high energy electrical currents pass through certain stones, they can rearrange crystal structures or create small fractures. Over long periods of time, repeated exposure to lightning can contribute to weathering, the gradual breakdown of rock that eventually becomes soil. Though the effect of any single strike is tiny, the accumulation of many strikes across large landscapes helps create the materials that support plant life. Another quiet effect of lightning is its influence on the atmosphere's electrical balance. The Earth carries a natural background electric field, maintained in part by lightning strikes around the globe. Every day, thousands of storms release millions of flashes, each one contributing to this global circuit. This constant rhythm, steady, persistent, almost heartbeat like, helps regulate the distribution of charge in the atmosphere. Even when we cannot see or hear a storm, lightning somewhere on the planet is gently maintaining this balance. Lightning also affects the behavior of clouds. By redistributing charge, lightning can shift the internal structure of a storm, encouraging new regions of condensation or altering the paths of updrafts and downdrafts. Over time, this influences how storms grow, move, and dissipate. Though these patterns are complex and subtle, they show that lightning participates in the atmospheric dance, not just as a flash of energy, but as a shaping force within the storm's life cycle. Above the earth, lightning reaches even into the upper atmosphere. Sprites, jets, and other high-altitude electrical events help regulate the electrical environment of the mesosphere and ionosphere. These delicate flashes influence charged particles, wave patterns, and the movement of energy between different layers of the sky. Over long periods of time, these subtle shifts contribute to the stability of the upper atmosphere, helping Earth maintain the conditions that make the surface hospitable to life. In some environments, lightning interacts with water. When a bolt strikes the ocean, the electrical current spreads across the surface rather than penetrating deeply. Though this generally does not affect marine life, it does create brief zones of rapid ionization, tiny changes in the chemistry of the water that dissipate quickly. Over many thousands of years, lightning strikes help cycle trace elements in shallow waters, contributing to the complex chemistry of coastal ecosystems. Even the presence of lightning can shape the behavior of animals. Some species can sense atmospheric electricity, responding instinctively to the approach of storms. Birds adjust their flight paths. Insects change their patterns. Certain mammals seek shelter. Over evolutionary time, lightning and thunderstorms have guided the development of these instincts, helping species adapt to their environments. Though subtle, these influences shape ecosystems, migration routes, and survival strategies. Lightning also shapes human history. For ancient cultures, lightning was often seen as a sign from the sky, a message, a warning, or a symbol of power. Many early civilizations built myths around lightning, weaving it into stories that shaped their understanding of nature. These stories influenced beliefs, rituals, and even early scientific curiosity. While these cultural effects are not physical, they reveal how deeply lightning has touched human imagination across generations. When we think of lightning as a participant in Earth's long story, as a force that shapes chemistry, supports ecosystems, records its path in fulgurites, and influences the rhythms of atmosphere and life, it becomes more than a sudden flash. It becomes a gentle presence, always working in the background. Each bolt is a brief moment, but over time, Lightning is a soft architect of the world, a patient contributor to the soil beneath our feet, a silent caretaker of forests, a quiet participant in the chemistry of life, a keeper of balance in the sky. And when we view lightning through this slow, expansive lens, it becomes a deeply calming presence, one that reminds us that even the most powerful bursts of energy can play gentle, nurturing roles in the story of the planet. Lightning is not confined to any one landscape or climate. It appears almost everywhere on Earth, from the warm equatorial rainforests to the frozen edges of the Arctic Circle, from vast deserts to dense mountain ranges, from open oceans to grassy plains. And in each of these environments, lightning expresses itself in slightly different ways, shaped gently by temperature, humidity, air movement, and the unique rhythm of each ecosystem. When we explore the world through the quiet lens of lightning, we discover how different regions give this phenomenon their own signature, their own soft footprint across the sky. Let's begin in the tropical rainforests, where some of the most frequent lightning events on the planet occur. The Amazon basin, for example, experiences incredible lightning activity because of the warm, humid air that rises constantly from the forest canopy. Moisture evaporates from vast expanses of vegetation, feeding towering clouds that grow rapidly throughout the day. These clouds collect enormous amounts of charge, often producing gentle distant flickers long before storms fully form. In these dense, lush environments, lightning often illuminates clouds from within rather than striking the ground. The moist air disperses the light softly, giving tropical thunderstorms a glowing, lantern like quality that spreads across the horizon. Moving westward across Central Africa, we reach places like the Congo Basin, home to some of the highest lightning densities on Earth. Here, the combination of intense heat, high humidity, and strong atmospheric instability creates thunderstorms that pulse almost daily. But the lightning in this region often feels serene when viewed from a distance. The storms build slowly over the canopy, their flashes revealing the patterns of towering clouds that rise like silent mountains above the trees. Even the thunder, though powerful, tends to roll gently across the endless forest, softened by vegetation and absorbed by layers of leaves and branches. In the savannas that surround these forests, lightning takes on a different character. During the rainy season, thunderstorms sweep quickly across the grasslands, creating wide, panoramic displays of cloud to ground lightning. The openness of the landscape allows bolts to stretch visibly from cloud to earth, forming long, bright channels that stand out against the vast sky. Savanna lightning often branches beautifully and is easier to observe than in dense forests. During the dry season, distant heat lightning flickers across the horizon, lighting the sky in soft pulses above the golden grasses. Though storms may be far away, their light travels effortlessly across the plains, creating a calm, nighttime rhythm of distant glows. As we travel into the deserts, lightning becomes rarer, but no less beautiful. The dry air tends to resist the formation of large storm clouds, but when storms do appear, they are often dramatic. In deserts like the Sahara or the Arabian Peninsula, dry thunderstorms sometimes form, storms in which lightning flashes across the sky, but little or no rain reaches the ground. The bolts appear crisp and sharply defined because of the clear, dry atmosphere. Thunder echoes across dunes with a long, rolling quality bouncing gently off distant sand ridges. And at night, lightning often illuminates the landscape with a clarity that feels almost otherworldly, revealing the contours of the desert in brief, quiet moments. In mountain ranges, lightning behaves differently still. The rugged terrain forces air to rise, forming clouds quickly. Mountains create their own microclimates, producing afternoon storms that develop with regular rhythm. In places such as the Rockies, the Himalayas, and the Andes, lightning often travels horizontally across the sky as storm cells form at different altitudes. Cloud to ground strikes are common on ridges and peaks, where the terrain rises closer to the storm's electrical centers. Yet from sheltered valleys, lightning often appears as a soft glow above mountain silhouettes, with thunder echoing gently through ravines, creating layered, calming acoustics. The grasslands and plains of North America, Asia, and Eastern Europe host some of the world's most dramatic but also most beautiful thunderstorms. On the Great Plains of the United States, for example, long sweeping storm fronts produce vast sheets of lightning that illuminate entire sections of sky. These anvil crawlers, as they are sometimes called, stretch horizontally for tens of miles, gently lighting the underneath of large storm anvils. The open terrain makes these storms appear majestic and expansive. Even when viewed safely from afar, the slow rhythmic flashes produce a hypnotic calm, an entire sky breathing with light. Over the oceans, lightning finds a different home. Water surfaces do not heat as quickly as land, so storms form more slowly. But when they do, oceanic thunderstorms can be vast. Maritime lightning often appears soft and diffused, as the moisture-rich air scatters the light gently. When lightning flashes over calm seas, the surface reflects the glow, doubling the beauty of the moment. Sailors and travelers often describe ocean lightning as peaceful, a distant shimmer that glows like moonlight. Heat lightning over the ocean is particularly common, creating silent, continuous illumination that blends seamlessly with rolling waves and horizon lines. In the polar regions, lightning is rare, but not impossible. Traditional lightning requires warm air rising into cold layers, but in recent decades, scientists have observed an increasing number of storms capable of producing lightning even at high latitudes. These thundersnow events occur when lightning forms inside snowstorms. The flashes reflect off snowflakes and icy crystals, creating a soft, muted glow instead of the sharp brilliance seen in warm climates. The thunder that follows is gentle and muffled, absorbed by dense snowfall. In the Arctic and Antarctic, lightning becomes a quiet curiosity, brief pulses of light within the tranquility of frozen landscapes. Volcanic regions offer one of the most dramatic and unusual settings for lightning. Volcanic lightning forms not in rain clouds, but in plumes of ash rising from powerful eruptions. The ash particles collide constantly, exchanging charges in much the same way ice and droplets do inside a storm cloud. When the charge separation becomes large enough, lightning sparks within the plume. From a distance, volcanic lightning looks like tiny, brilliant threads woven through dark, billowing clouds of ash. The contrast between the bright bolts and the black plume creates a breathtaking, almost surreal scene. And yet, even in this dramatic environment, the principles behind lightning remain gentle. charge separation, ionization, and the search for balance. In coastal environments, lightning behaves in unique ways due to the interaction between land and sea. Sea breezes can trigger afternoon thunderstorms as warm land air rises and cooler ocean air moves in to replace it. These coastal storms often produce spectacular displays of sheet lightning, illuminating clouds that drift slowly offshore. The combination of warm humidity, stable air masses, and gentle breezes creates storms that are visually stunning, but typically less intense than inland systems. The result is lightning that flashes softly over the water, spreading warm reflections across calm ocean surfaces. In temperate forests, lightning shapes the rhythm of the seasons. Storms are common in late spring and summer, when warm air rises through layers of cooler atmosphere. The lightning here often appears subtly, illuminating leaves and branches in fleeting patterns. The canopy diffuses the brightness, creating soft pulses of light that ripple across the treetops. When thunder rolls, it is cushioned by trunks, moss, and soil, producing a muted, comforting sound. Every ecosystem on Earth gives lightning a new context, a new character, a new tone. But beneath these differences lies the same set of gentle principles. Lightning expresses the atmosphere's search for balance, shaped by temperature, humidity, terrain, and the subtle interplay of natural forces. When we view these variations from a calm perspective, lightning becomes a tapestry woven across the globe, each thread reflecting a particular climate, a particular landscape, and a particular mood. And in every environment, from deserts to oceans, from tundra to tropics, lightning offers moments of quiet beauty, moments when the sky lights up softly, moments when the world seems to pause, moments when nature reveals its delicate patterns through brief, glowing strokes of energy. Lightning, despite its beauty and quiet scientific elegance, is also a powerful natural force, one that living creatures, landscapes, and even human societies have learned to sense, anticipate, and avoid. This instinctive awareness is not rooted in fear, but in adaptation. Over millions of years, life has developed subtle ways of detecting the early signs of electrical storms, tuning in to the atmosphere's signals long before the first flash appears. When we explore how nature and humans sense lightning, we uncover a world of gentle cues, quiet warnings, and the delicate relationships with the sky. Long before lightning strikes, the atmosphere begins to change. The air grows heavier with moisture. The wind shifts direction. Temperature, layers shift and swirl. And perhaps most importantly, the electrical field near the surface of the earth begins to strengthen. All organisms live within this field, even if they don't consciously notice it. Some species, however, are especially sensitive to these subtle changes. Animals, for instance, have evolved remarkable ways of sensing approaching storms. Birds can detect shifts in barometric pressure, which often drop before thunderstorms form. This allows them to adjust their flight paths, seek shelter, or remain grounded when storms approach. Their sensitivity is so fine tuned that many birds change behavior hours before lightning ever becomes visible. Some species choose to stay hidden deep within foliage, while others move instinctively toward more stable terrain. Insects, too, respond to storms with surprising precision. Bees often return to their hives earlier than usual when atmospheric pressure falls. Butterflies settle in sheltered areas. Ants build up their mounds and cover the entrances. Although tiny, these creatures sense the energy in the air, the rise in humidity, the charge separation, and the subtle shift in the electric field. Their movements are guided not by conscious thought, but by deep rooted instincts shaped by thousands of generations living under the sky's rhythms. Larger animals have their own strategies. Elephants, for example, are believed to detect low frequency vibrations caused by distant thunder through their feet. These vibrations travel through the ground long before the sound reaches the air. Elephants feel the tremors and adjust their movements accordingly, often seeking safer terrain before storms intensify. Many mammals, from horses to deer, show restlessness as storms approach, sensing a combination of pressure changes, electric fields, and distant vibrations. Plants, though silent and rooted, also respond to storms. Before rainstorms, humidity rises sharply and the electrical field strengthens. Some plants react to these changes by altering the opening of their stomata, tiny pores in their leaves. Others shift the chemical balance of their cells in preparation for incoming rainfall. While plants do not sense lightning in the same way animals do, they respond to the conditions that make lightning possible, participating subtly in the atmospheric dance. Humans, too, have an innate sensitivity to storms, though our awareness is often overshadowed by distractions of modern life. Before advanced technology existed, people paid close attention to signs in the environment: darkening skies, changes in air pressure, the smell of ozone, and shifts in wind direction. Indigenous cultures around the world developed detailed knowledge of storm behavior, learning to interpret nature's signals with remarkable accuracy. They recognized that lightning was part of a larger atmospheric system, one that could be read if one moved slowly, attentively, and respectfully through the landscape. Even today, our bodies respond to storms in subtle ways. Some people experience headaches or pressure sensations as the barometric pressure changes. Others notice the air feels heavier or still. Occasionally, the fine hairs on the skin may lift slightly due to static buildup in extreme electrical fields, though this is rare and generally precedes lightning strikes that are dangerously close. These sensations are reminders that even when we're indoors, we remain connected to the atmosphere around us, living within the same electrical environment as every other creature on Earth. Modern technology has expanded our ability to sense and track lightning in ways our ancestors could never have imagined. Sophisticated tools, such as lightning detection networks, capture electromagnetic pulses from strikes in real time, mapping their locations across continents. These systems rely on the fact that lightning emits a unique pattern of electromagnetic radiation, which can be detected from great distances. Scientists and meteorologists use these tools to understand storm behavior, monitor global patterns, and help predict severe weather events. Even so, the act of sensing lightning is not purely a technical feat. There is beauty in the simplicity of nature's cues. One of the most delicate signals comes from the way the air feels moments before a lightning strike. In extremely charged environments, small ions build up in the atmosphere. Some people describe the sensation as a metallic or clean smell. This is ozone, created when lightning or strong electric fields interact with oxygen molecules. The scent is subtle, appearing only briefly, but it is one of the atmosphere's quiet warnings that lightning is near. Thunder provides another soft signal. Even when lightning is far away, the distant rumble tells us the storm is approaching. The rhythm of thunder, the spacing between its rolls, gives clues about distance. A long gap between flash and rumble means the storm is far. A short gap means it is closer. Throughout human history, people have used this natural timing to gauge safety long before instruments existed. When lightning does approach, nature offers gentle cues. Birds fall silent, leaves still beneath sudden, heavy air. The wind may pause abruptly before shifting direction. The sky darkens subtly, often in layers, pale gray at the edges, deeper and more complex in the core of the storm. Even water reacts. Lakes and ponds sometimes become strangely smooth, as if the air itself has pressed down upon them. These signs are not frightening. They are part of a natural system of communication between the Earth and its atmosphere. Humans have developed safe practices over time to coexist with lightning. Though the phenomenon is beautiful, it must be respected. Most safety measures are simple, grounded in calm awareness rather than fear, seeking shelter indoors, avoiding open fields, giving distance to tall, isolated trees, and staying away from water during storms are all ways of honoring the power of lightning without seeing it as a threat. Many of these practices align with the instincts of animals, instincts that guide them to shelter, dense foliage, caves, or inner forest areas where lightning risk is lower. Interestingly, lightning safety also extends to the design of our homes and cities. Lightning rods, first popularized by Benjamin Franklin, provide a safe path for lightning to follow, guiding electrical energy harmlessly into the ground. These rods do not stop lightning, they simply offer it a gentle, low resistance route. In many ways, lightning rods mimic nature itself, providing pathways that help maintain balance without disruption. On a global scale, scientists study lightning not only to protect people, but to understand the deeper rhythms of weather, climate, and atmospheric chemistry. Lightning frequency varies across seasons and decades, offering insight into how Earth's climate is shifting. As temperatures rise, some regions are expected to experience more thunderstorms, while others may experience fewer. Understanding these changes helps us appreciate lightning not only as an atmospheric event, but as a messenger, one of the many natural indicators of the planet's evolving climate patterns. Yet, despite all this knowledge, there remains something quietly mysterious about lightning's presence, something ancient, something that bridges the gap between science and intuition, the way animals sense storms, the way humans feel the air shift, the way the sky communicates its intentions through subtle cues. Lightning is both a physical event and a natural language, one spoken softly through pressure changes, electric fields, wind patterns, and light. When viewed through this gentle perspective, lightning safety becomes less about fear and more about awareness, a calm respect for the atmosphere's energy, a recognition that storms follow patterns that can be sensed, understood, and anticipated, and a reminder that even the most powerful forces of nature often reveal themselves quietly long before they fully arrive. As our quiet journey through the world of lightning comes to an end, allow the last remnants of these soft facts to settle gently in your mind, like distant flashes fading beyond the horizon. You've traveled through clouds, across continents, through the upper atmosphere, and into the deep history of the earth, guided not by urgency, but by curiosity, calmness, and the soothing rhythm of natural science. In each chapter, lightning revealed itself not as a force of disruption, but as a quiet participant in the planet's balance, a pulse of energy moving gracefully through the sky. Now, as you rest, you don't need to hold on to every detail. Let the information drift, the way clouds drift after a storm. Let the ideas soften, like thunder rolling gently into the distance. Everything you've heard tonight has been a gentle reminder of how nature moves, slowly, steadily, with purpose, and always returning to calm. Feel your breath deepening. Feel your body settling into stillness. Notice how each muscle unwinds a little more with every slow inhale and soft exhale. The storm you explored was never one of chaos. It was one of balance, of connection, of quiet beauty. And now that storm has passed, leaving behind a peaceful sky inside you. Allow your thoughts to grow lighter, drifting like mist. Let your awareness dim, like the fading glow of a cloud illuminated from within. There is nothing left to do and nowhere left to go. Just rest, breathe, and let sleep rise to meet you at its own gentle pace. Lightning, in all its brilliance, has guided you through the night. Now, let the calm that follows guide you into dreams. Good night.